So, good afternoon, everybody. I hope you're enjoying yourself at the conference. Welcome to my talk on WebRTC Security. So I'm giving this talk because I think WebRTC is really an important change in the field of the web and the web architecture. And I hope throughout this presentation you will have the feeling how it actually disrupts the whole way we are interacting with the web. So a little bit about myself. I'm Lieven Desmet. I'm a research manager at the University of Leuven, where actually I'm coordinating a team on application security. All researchers on web application security in the broad. I'm also actively engaged in OWASP. I'm a board member of the Belgium chapter, and I also co-organized the European conference back in Amsterdam in earlier this year. And I'm also the program director of SecRDev. This is a yearly week-long training on secure application development, which has already been running for more than 10 years. But back to the presentation. So what I want to do in this presentation today is giving you a very good glimpse at what is WebRTC all about. I will present it first high level from an architecture point of view. Then I zoom into the communication protocols and also to the JavaScript APIs that are available to developers. And I hope after this part, everyone will have a good enough understanding of WebRTC to understand the reporting I will do on the security and privacy of an assessment we have been doing on WebRTC. But maybe to get a little bit of feeling of the audience, who of the audience already was developing in WebRTC technology? Only a few hands. Who's actually planning in the next 2 years, to integrate some WebRTC technology in their websites? Some more, let's say 15–20%. Okay, maybe another question. Who is here for the WebRTC part? Who is here for security? Who is here for the WebRTC part? The majority. Security? Almost all room. So both parts are actually present in the presentation, so that's good. So, but first, WebRTC. When you would ask me what is WebRTC all about, actually I would say it's really a disruptor within the web architecture, because now all of a sudden peer-to-peer connections become available in the web architecture. But if I take one step back and I need to explain to a layman what is WebRTC, well, I would say we have been using all kinds of technology in the past to have audio and video communication over the web. Think about WebEx, GoToMeeting, Adobe Connect, Link, FaceTime. And now all of a sudden, all that technology becomes available from within your browser. So now with WebRTC, there's no need to install any extension, any plugin within your browser. All of a sudden, everyone can participate in a peer-to-peer connection in an audio-video conference setting. And this is a screenshot of a few years back when the first Chrome and Mozilla browsers were communicating to each other on WebRTC. So and it's as simple as you see it right here. You're using your plain browser, you're using the technology in your browser, and you're able to set up video and audio communication with other parties on the internet in a peer-to-peer fashion. So summing up, you're actually having peer-to-peer browser communication. You have the ability to route audio and media streams across those peer-to-peer connections, and everything is fully JavaScript empowered. It means you can actually build the whole application within JavaScript using the building blocks available in your browser. Of course, it means that the whole protocol stack is available within the browser to enable the WebRTC communication. And I will first zoom in a little bit what are the communication protocols in the browser being used to enable WebRTC. So from a very, very simple view on the WebRTC architecture, you have two browsers that want to communicate in a peer-to-peer fashion. They will all load code from a central web server. So this is a very classical paradigm in the web. A browser is actually connecting to a web server, is downloading JavaScript code and runs it within the browser. This is step one, and typically you're using that over HTTPS. The next step is that the browser will now initiate a direct communication to the other peer and do that with DTLS and SRTP. So it means now all of a sudden your browser is not only communicating to a server, but now is communicating to other browsers on the internet. And this is a very simple view. You have two parties involved in a communication model. But of course, there are multiple deployments possible with WebRTC, and also the specifications have made up so, in this way that it's very liberal the way you will use WebRTC in the future. So for instance, the simple one is a two-party video conferencing stream. You have one central server, you have two browsers communicating with each other in a peer-to-peer fashion. But you could also have the example where the browser is actually having a peer-to-peer connection with the server itself. So think about an e-commerce website. Nowadays, you can already chat with some employees of the e-commerce site. Now, all of a sudden, you will have an extra button where you can start a video conferencing with an employee at the e-commerce shop. And this is kind of the help desk call scenario. But you could also have it in a federated way. You don't need to stop with one signaling server. You could have multiple signaling servers cooperating together. You could, for instance, use Google as one server to log in. Another user is using Facebook. And in a federated setup, they're using a peer-to-peer communication between the two users. And you're not limited to only connecting to browsers. You could imagine that one of the servers is actually a gateway to existing SIP installations, to existing XMPP infrastructures. So in that sense, you could have a bridge set up where you have your browser suddenly communicating with voice over IP phones over the web. And this is only when you have two peers involved. You could also have multiple peers involved. Rather than the two-peer scenario, you could have, for instance, 4 peers, and you can communicate in different ways. For instance, this is the mesh network. Every entity is communicating to every other entity in the communication. But you could also say, well, one of the browsers is actually the master, and in a star network, everything gets rerouted via that server or via that client. Or you could use dedicated hardware, such as a multi-point control unit, to reroute all the streams and from there on dispatch them to all the other browsers again. Again, WebRTC is very liberal. None of the specifications does any limitation on how you use the technology. And also for a security perspective, this is important because it's so unconstrained. There are also very, very ways you can have a look at your particular infrastructure, how it could be attacked. This is the basic view. So we have two peers that want to communicate over the web. And for the rest of the presentation, I will limit myself to 2 peers that are connecting, but take into account that you can have multiple peers connecting in a mesh or store or any other configuration. What are now the communication protocols being used in WebRTC? Well, we first saw the signaling part. The signaling part is actually the communication via the classical server. So the client connects to the server might have a connection to other clients. This is called the signaling part, and what it does, it loads the client-side context, the code of JavaScript running in your browser, and it also reroutes or mediates all the control messages and metadata. So in order to set up a connection, some information needs to be exchanged between the two endpoints. All that communication is routed via the web server, via the signaling path. And what's important in the context of WebRTC is that in WebRTC, the whole signaling protocol is undefined. So it's actually up to your own application to decide what is the best signaling protocol to use. How can we actually integrate and communicate bidirectional between the browser and the central servers? In the examples I will use later on in my presentation, we're typically using socket.io, but you could also use WebSockets. You could use any other means of bidirectional communication between the client and the server. On the media path, it's much more streamlined. There we actually want to set up a secure peer-to-peer connection between browsers for media streams, audio and video. I didn't mention before, you can also send data, so you can actually send strings from one entity to another in a peer-to-peer fashion. The protocols being used there are DTLS, and you can think about DTLS as UDP with all the characters of TLS. And on top of DTLS, in order to have real-time communication, secure real-time transport protocol, SRTP, is being used. So these are the building blocks that are already present within your browsers, which enable you to communicate with other parties. I will not zoom into how actually DTLS-SRTP is working. This is out of scope for the talk. What I will focus is in how you actually configure those protocols to being used in a WebRTC communication. And this is actually kind of challenging. In order to set up the media part, we need to do 2 things. First, we need to exchange all the parameters in order to configure our 2 endpoints to be able to see the same video streams, audio streams. So that is actually done by exchanging media parameters. And the second part is actually exchanging network parameters. How can we make sure that we can make a connection from browser A to B across firewalls, NATs, and so on? And any of the technologies being listed here is not new. They're actually being borrowed from previous infrastructures, for instance, from SIP. So now I zoom a little bit into how I exchange media parameters, how I exchange network parameters, and then we can zoom out again to see what does it mean from an architecture point of view. So the first step is the session description protocol. It is actually exchanging data about what kind of media types you're willing to accept, what kind of codecs you have, all the information about your screen real estate, what kind of media can I actually consume or produce on my device. And it works with an offer and an answer. So a browser will typically send an SDP offer to the other side. It will receive an answer, and from that point on, you know what are the capabilities of the other side. And to send around the offers and the answers, you're using your own custom protocol via the signaling server. The signaling server has to make sure that the data from browser A reaches browser B and vice versa. The way the messages are structured, those are present in the specifications. They are all actually standardized. And to give you just a glimpse of what an SDP offer looks like, this is an example taken from the specifications. And you will see it's actually one large text-based file. You have kind of key and pair values. And that's also the interesting part within processing such a data in a JavaScript context. We would expect that data to be available in JSON formats or the like. But because we're actually borrowing those technologies from the SIP world, this is fully text-based, and we will also see parsers and also mistakes and bugs in the parsers to actually process this kind of data or tamper with that data. This is the part on media exchange. We don't need further details at this moment. For the networking part, I can actually say the main part of the networking, which is actually the challenging part, is making sure that there's connection between the two peers. The peer-to-peer fashion, which is actually central in WebRTC, needs to cope with firewalls and nuts in between. How does it do that? It uses UDP hole punching. And the main idea of UDP hole punching is you're actually making a connection to a public server. At that moment, a public UDP port is opened on your NetEnt firewall. If the other side is actually doing exactly the same, all of a sudden you can have communication between A and B, although there are firewalls and nuts in place. This is the most optimistic scenario. This will not work with any firewall, any nut being present in your infrastructure, but this is the main idea how to connect in a peer-to-peer fashion between browsers. So when do you have to use which kind of technology to enable the networking part? In order to know which is your external IP, your external port, that public server I showed you in the UDP hole punching, you're using a stun server. You're actually able to communicate to that server, and that server will tell you, this is your external IP, this is the port that is being opened. This is the optimistic scenario. Both parties using a stun server, and they're able to set up a connection. In case that is not working, you might need to fall back to a turn server. And what the turn server does is actually playing a relay. It will relay for you all the connections between two peers that are not able to communicate directly. So it will actually take packets from one side and send them to the other side. And to exchange data about stun and turn from side to side, you're actually using the ICE protocol, which actually will give you a list of possible stun and turn alternatives from one side to the other side until you find a match between the two networking points. Not so important how we actually configure the stun and turn server at this moment. What's important is that actually the architecture picture we had before, which was very, very simple, is now getting more and more complicated. Now, all of a sudden, in order to set up a communication between two browsers, we need also to involve stun servers, turn servers, and exchange ICE information between browser A and B via the signaling path. But as you will already have noticed, the picture is really in the top part of the slide. There's still a lot of open space. Well, there's actually one more thing I need to tell about the WebRTC architecture, which makes it a little bit more secure. And this is about identity provisioning. In order to communicate with a third party on the internet, you actually want to know who is at endpoint. You want to authenticate the endpoint. And in order to do that within WebRTC, you're falling back to identity providers. You're asking identity providers for you to assert a user and to verify the identity of a user. How do you do that? The browser will load in a very dynamic way code from the identity provider. It will ask the identity provider to get an identity assertion. The browser B will receive that assertion. It will ask the identity provider to verify that identity assertion, and only if that matches, there will be an authenticated channel between browser A and B. And in this way, I can actually know that I'm talking from John of Facebook or Magai from Google. And this is the way it will work within WebRTC. If I look what is actually done within the browser itself, you're already having the red code running in your browser coming from the web server. This is the original code that is actually running the whole WebRTC part. Now you will ask the WebRTC APIs to load an identity provider. It will fetch code from the identity provider, run it in an isolated environment and call that an IDP proxy. And this is actually done in a realm within JavaScript. And then you will communicate with web messaging to the realm to ask for an identity assertion or to verify an identity assertion. And this completes the full architecture picture we have about WebRTC. every party can use his own identity provider to get identity assertions, and you need to verify each other's identity assertions with the identity provider of the other party. And this is actually all the stakeholders that are involved within a very simple case where browser A and B want to communicate. And this is also the protocol stack I was talking about. This, of course, is mainly hidden within the browser. That's the good news. Now we actually will look how a developer communicates with all those building blocks within the browser. So I will give you a glimpse of the JavaScript APIs. It's not my intention today that I learn you how to program WebRTC. There are very good tutorials on the web where every different step can be actually looked into. I just want to give you a glimpse of what is programmable within WebRTC and what is the difference between custom protocols and the things that are already available from WebRTC itself within the browser. I think it's fair to say that the WebRTC building blocks are very well represented already in the browser. It means with like 200 lines of code, you could have already a functional demo of two parties communicating over the web. And that's client and server code all integrated in one. So I already said the whole WebRTC is fully JavaScript empowered. It means that the JavaScript APIs are exposing all the functional blocks within WebRTC. You're able to set up peer-to-peer connections. You're able to handle audio and video streams. And you're also exchanging the SDP Office ICE candidates. So they're actually present as objects within the JavaScript environment. And now a few glimpses on the APIs to be used. For instance, in order to set up an RTCP connection, you're just making a new RTCP connection within JavaScript, give it some parameter configuration about, for instance, ICE service, stun servers, turn servers, and all of a sudden it will start set up a peer-to-peer connection. What it will do is actually call event handlers for the SDP and the ICE candidates, and that's the next step I will discuss and show within the slides. So in order to exchange SDP offers and answers, the browser will trigger event handlers to say, well, this is the SDP object you need to send to the other party, or this is an SDP object you received from another party. And so the browser will actually trigger those events, and then you will have to send them for yourself via application-specific signaling. So whatever is in purple within my slides is your own channel you have to make to communicate to your web server from point A to B. So that is actually making sure that all the data you want to give to the other party is being relayed via the web messaging. The red parts within the slides are the APIs and the handlers already present within your browser to handle the receiving of SDP and ICE, or to emit ICE and SDP candidates. So these code fragments are sufficient to exchange data that the connection will happen, so that you have all the SDP information already exchanged between the two parties. In order to set up the network connection, you will have a very similar way where you're actually exchanging data about the network specifics. So here again, all the network specifics about what is your IP address, how to communicate, what are the different protocols you support. This is all realized by the browser. The only thing you need to do is actually getting them from an emitter and send them to the other party and vice versa. And this is the way you're actually programming the whole WebRTC part in your web application. So again, the exact APIs are not part of this presentation, but you get an idea of how complex the code is to actually set up a complete WebRTC scenario. So by the things that we showed until now, we actually have already a full peer-to-peer connection between the two endpoints. Of course, having a peer-to-peer connection but not using it for anything useful within your application is not so interesting. So the next step is actually making sure that we can have video from our camera and that being sent to the other party. So what the first thing is to do, we will actually ask the browser for permission to get our camera or user media. And once it actually approved, gives consent to get our camera, we can actually send that around at the stream to our peer connection, and all of a sudden that video stream will also reach the other party and he can receive it and consume it. And actually WebRTC technology is as simple as that. You only have a few APIs you need to implement in order to make a full WebRTC communication. Similarly, you can do that for data channels, and in the end you have a way to communicate peer-to-peer, and it's up to you to be disruptive in the way you're using that application. For instance, you saw already file transfer applications. Now all of a sudden you have file transfer application between two peers where your file will never be stored on a central server. You have already very easy communication platforms like Talkie, where you can actually already, given one URL, interact in a kind of video conferencing without pre-processing, without pre-configuration. And this is only the first step. These are the building blocks within your web application. Good. I think this is the basic part I want to mention about WebRTC before going into some of the details of our security and privacy analysis. So if you have any question about the WebRTC protocols, the architecture, or the APIs, this might be a good time to actually come forward and ask you some of the questions, because they might actually be necessary to understand the rest of the presentation. It does work. So the question was, does it work on mobile? Yes, it does work on mobile. So we had some tests last year in a lab where we were using an iPhone and an iPad to communicate with WebRTC technology. So it depends a little bit on the maturity of each of the browsers, how far they go, of course, in supporting each of the features. But the basic setup, having real-time communication, is already available on mobile. So I would say, from what I saw, what I presented here in the architecture, the main part that most of the browsers do not support or not support at all is the part on identity provisioning. And I will also discuss later on why this is really a tough problem within WebRTC. Any other question?
How does this security exactly work, this identity provider? Is it with a private public key?
So the identity provider, I will discuss it in more detail. And so the question is, how does the identity provider exactly work? And I will discuss it a little bit later in my presentation in more detail. But the idea is you use an external web application, and you're interacting with that web application to know whether or not you're a particular user. So you will get an assertion type out, and you could use that assertion and give it to the other party to show that you're really that identity. But I will show it and cover it in a little bit more detail later in my presentation. Good. Then I actually will go to the more security and privacy part of the WebRTC. And I think it's important, if it's reporting on a security assessment, that we're saying which are the attackers we had in scope while doing the assessment. So the first attacker we had in scope while doing the assessment was the attacker residing on the network attacker. He's able to observe and tamper with any network traffic coming around. So if the Wi-Fi is working here, imagine anyone here that is actually tampering with the Wi-Fi while you're communicating. What is the impact of that network attacker on your WebRTC application? What is the impact on the end users? The second attacker that we had in scope is the malicious web server. So that is the servers, and it could be more than one server if you have a federated setup, that is actually sitting in line on the signaling path. It sees all the control and metadata messages, and it can tamper with each of those messages. And it also controls the client-side JavaScript code. So why did I include this attacker in the model? If you're looking from the standpoint of view that you say, I want to make up a WebRTC application, of course, you will not be the malicious web server. But you also need to take into account what is the impact of anything bad happening on my server to my users. Especially because users are expecting, if you have a peer-to-peer connection, that there is some privacy guarantees. So they're not expecting that anyone can observe the communication that's going on between party A and B. And in the same line, and maybe more practical, is the fact that you also have malicious third-party JavaScript running in your application. So even if you're not malicious at all with your application, you could have some JavaScript embodied in your application that is doing malicious stuff with your web application, with your WebRTC application. And it can be either included deliberately because you're using all kinds of APIs, you're using Google Analytics, you're using the Facebook like button and so on. Those libraries might be compromised. It could also be that it's injected because you had, for instance, a cross-site scripting vulnerability on your website. And what's important with this attacker model actually runs in the same JavaScript context as your WebRTC code. It can actually interact with all the APIs. It can actually see all the data flowing by in any of the APIs you're using for WebRTC. So those are the three network attackers. It's also fair to say that in our assessment, we always took the side of the end user. We wanted to protect our end user as good as possible within the WebRTC context. And so in our analysis, we have three parts. We have an overview of the general observations. If you're looking to the architecture, what are the conclusions that we can draw from WebRTC? I have one part that is discussing the security impact of this technology on websites that are actually using WebRTC. So what are the weaknesses when you're embodying WebRTC? What have you to take care of? What are the best practices? And I also have a part on what is the security impact of WebRTC being present in your browser, even if your website is not using WebRTC. So you have a legacy website up and running right now. What is now the issue of browsers all of a sudden being capable of running WebRTC? But I will start first with the general observations. So, and one very straightforward general observation is, of course, that the attack surface did change over application. Where in this architecture in the past, all communication was happening between the browser and the web server, now all of a sudden communication is happening between the two browsers directly without any server being interacting with them. This also means that all of a sudden, all the parts we were typically doing at the server side, like input validation, like sanitization, now also have to be transferred to the client side for client-to-client interactions. We can even go one step further. We could even use the remote party where we are sending data to attack their web server. So when the web server gets attacked, it's no longer the case that that particular browser might be malicious. It could also be that the peer-to-peer connection is being used as one step to send the malicious payload to the other party. And this is something that we need to adapt into the web architectures field, because we are not used that communication is happening directly between two endpoints. We are so used to client-server paradigm also in securing our applications that now all of a sudden we have to think about another port to interact with our web application. A second general observation was one that we made while we were actually assessing what is the WebRTC permission model. And when I say permission model, I actually mean to what operations within WebRTC do you as an end user have to give consent in order to run them in your browser? For which of those operations do you actually have a visual indicator that those operations are being executed on your behalf in the browser? And in order to actually go over the different characteristics, it might be good to do some kind of a little quiz within this audience. So I would propose, whenever you think that you would like to be involved as an end user when this operation executes in your browser, just to raise your hands, and then we have a little count on how many people actually think this is important to be informed about, to actually control that within your browser. So the first thing is, do you want to be involved when the camera is actually being executed or used within your application? Of course, most of the people, well, I have good news. It is actually the case that for any interaction with your camera, the user media that you saw before, it will actually pop up a small dialog asking the user, do you want to give consent to use the camera? Be aware that for camera and microphone, it depends on the implementation of the browser, but in a lot of cases, if you're using HTTPS, the consent will be kind of permanent. You give it now, but it also is for the next hour, for the next 2 hours, and so on. Okay, next question. Do you want to be informed of on control if some network characteristics like your local IP addresses, your VPN address, and all the others are collected from your browser? Some people are actually waving their hands. It's smaller than when I typically talk in a security audience, but unfortunately, you will not be informed, or you don't have any control that network parameters get resolved within your network browser. If a peer-to-peer connection is being set up between two endpoints, do you want to be informed that a peer-to-peer connection is being set up with another party in a peer-to-peer fashion? What do you think? I think a large majority. Unfortunately, this is completely behind the scenes. So you don't have any control in your browser, you don't have any dialogue informing you that the peer-to-peer connection is being set up by the JavaScript context. Do you want to be informed that your audio video is being sent to a remote peer? Majority. Actually, you're not informed. As soon as you give permission to an application to use your camera and your microphone, it can reroute that stream, and on their behalf, they don't need any consent to ask where that video needs to send to. So with peer-to-peer technology in the browser, all of a sudden you have your camera to do all kind of funky stuff locally on a website. Now JavaScript can send that video to any party on the network. Sharing your screen. Everybody, almost everybody. I have good and bad news. The good news is it's not part of the WebRTC specifications. So it means that out of the box, browsers do not support to share your screen because they feel that it's too sensitive, too critical to send your whole screen state, because you could have password managers or other things open on your screen. So in that sense, it's not available. On the other hand, they see the urge to be able to do that, and the way the specifications actually handle this at this moment is that it's up to the user to install an extension that provides capabilities to share your screen. So the extension model, for instance, of Chrome allows an extension to capture the whole screen as one of the permissions. And that extension could then expose that capability to the JavaScript context. So it's actually up to the user to install such an extension, but whether you will be informed or need consent on a per website basis really depends on the implementation of your extension. But at least it's not de facto already present in your browser when you're starting up your browser. So it's up to the extension that you're choosing to share that feature. Do you want to be able to select an identity provider? Well, you're not able to select any identity provider. You're even not able to verify that the endpoint you want to communicate to with the IDP is actually the endpoint you have in mind. I already mentioned the IDP is being used to know that you're certainly talking to a certain person of a certain identity provider. Well, the browser will check that for you, but you're not able to see what identity you're exactly talking to because it's all hidden within the JavaScript context. Your application could expose that to the user, but your browser will not expose that identity to the end user. And this is actually the permission model. If you're looking to the permission model of WebRTC is very liberal. It means it can actually do anything it wants within your browser context without actually needing explicit consent or need to dialogue with you to say we are doing this or this party. I think this is good to make sure that the technology can be used in a very user-friendly way. You don't have to click 3 or 4 dialogues in order to start up a peer-to-peer connection. But it also means, apart from the camera and microphone, you don't have any control of functionality being triggered in your browser. And especially for some of the text we will see later on, this is very important to understand that this is the permission model currently within WebRTC. So these were my general observations. Now I would like to go one step further and to look into what are the caveats when you're actually running your own website and you want to run WebRTC technology in your website. And I want to do that in 2 steps. If you're talking about communication, there are 2 aspects of privacy. First, you want to make sure that the fact that you're communicating is hidden, that nobody knows that you're communicating to another party. The second part is you want to make sure that the communication itself that cannot be eavesdropped on. So the first part is really focusing who does know that certain communication is happening within your WebRTC infrastructure. And if you're looking to the architecture picture again, you see several traces where people can note that communication is happening between browser A and browser B, or let's say user A and user B. So of course the signaling server, because the signaling server is handing over all the information, SDPs, ICE information between the 2 parties. It's actually helping to set up the communication. It can actually view which users are communicating to each other in a peer-to-peer fashion. If you're using a turn server, it actually has the information about the 2 parties that it tries to relay. If you're using a stun server, well, the stun server might be able to relate 2 different requests together to a dialogue, but it's much more difficult. So for a turn server, it's quite easy to observe that you have communication. For a stun server, it's a little bit more difficult to observe that pattern. The third-party JavaScript actually has the same properties as the signaling server within your JavaScript code. If it's also monitoring all the APIs being called in WebRTC, it can actually quite easily see that your browser is communicating to a third party. And similarly, the identity provider, if you create assertions, if you verify assertions, you can link both together and see which parties are actually communicating to each other. And this is important, especially in the case where telcos were tackled in the last few years, because they were actually exposing, for instance, to governments that communication was happening between different entities. Now, all of a sudden, you don't need to actually infiltrate a telco to know that information. If you're infiltrating a popular library like Google Analytics, all of a sudden you can know from the whole world who is communicating with what other person in this setting. And this is something that you need to take into account. The metadata is just kind of public within WebRTC. Whereas you have a private conversation in a peer-to-peer fashion, most people think that that communication will be totally private. You need so many stakeholders to set up your communication that all those stakeholders can leak information about the fact that you're setting up communication. So you can't compare WebRTC with Tor or with any other BitTorrent or any other sharing platform, because here you're actually exposing a lot of details about yourself and about the other party in order to set up the communication. But more important, let's focus on what happens if you want to actually eavesdrop and hijack the connection between the two parties. You want to see the video that party A is sending to party B. And we first look in what can a network attacker do, and then we will focus what can other parties within the infrastructure do. The first part is network attacker. The network attacker, the only way to actually eavesdrop on the connection is to set up a man in the middle. The man in the middle would actually interact to browser A as if he was browser B, and the same with browser B as if he was browser A. And such a man in the middle is actually very hard to achieve in the WebRTC world because the communication protocols are well defined. Actually, DTLS already provide encryption, message authentication, message integrity, and the fingerprint of the certificate which you want to communicate is already exchanged in the SDP information. So as long as you cannot interact or tamper with the SDP information, the browser will actually see that there's a man in the middle in between and will not set up the peer-to-peer connection. So from the networking point of view, WebRTC is very well protected. It was not able to set up a man in the middle between browser A and browser B. Unfortunately, this does not hold for the signaling components. This does not hold for the web server involved, for the third-party JavaScript involved in your application. So again, if we see the same architecture picture, what happens typically if you set up the communication? You're getting information about the network information from the stun server. You have your own certificate you're using for peer-to-peer connections. You're bundling all that information as part of the fingerprint within SDP. You're sending around that to the other party. But any party on that signaling path can change the SDP by its own SDP. And from then on, you can have a man in the middle, because what the browser will do is check or verify that the information of the certificate of the man in the middle matches the browser certificate mentioned in the SDP. And if that matches, it will actually have the connection in a man in the middle fashion. So you actually are able to set up a man in the middle as soon as you are able to tamper with the SDP information. So the only persons that only entities that can do that in the architecture, or the web server, the signaling server, or any third-party JavaScript running in one of the two contexts, can actually tamper with the SDP information, can tamper and set up a man in the middle. Maybe important also to say, the man in the middle scenario is not the most important scenario to eavesdrop on the connection. Another interesting attack that we saw during our assessment is that we are able to clone an existing video stream and send that over another peer-to-peer connection to a remote party. So instead of actually being in between browser A and browser B, as soon as we are controlling the JavaScript context of one of the browsers, we can say clone that video stream, clone that audio stream, and attach that to another peer-to-peer connection, for instance, with the attacker endpoint. So even if the normal connection is happening between browser A and B, JavaScript can now actually trigger that the same video streams, the same audio streams, local and remote, all get rerouted to a third party. And this is actually a very simple way to interact with WebRTC infrastructure and actually to eavesdrop on the connection. And this is also one of the best practices that you need to take into account. If you're running your own WebRTC infrastructure, make sure that you're not running third-party JavaScript within your application. Isolate it in a different domain and make sure that no third party is running your application, because this could be the impact of third-party software running in the application. So for the part of the man in the middle, actually the identity providers will come and help you. For the part of the JavaScript, there's no other help than saying, well, make sure that there's no untrusted JavaScript running in your application, a good best practice for any web application. So for the man in the middle, to actually tackle that, you're using endpoint authenticity. What does it mean? You're actually involving the identity provider. So we start in a very similar scheme as before. You have your network information, you have your certificate fingerprints, and now you're actually using the identity provider to, based on your identity, make a signature on the key store on the stun information. You're actually getting a certificate from your browser that is now labeled by a third party saying this certificate is really coming from Lieven Desmet. And at that moment, you're actually able to send that around to the other party together with the signature. And if you want to change that, it will never match the signature of Lieven Desmet. So the browser is able to detect that someone along the path did change the signature of that particular SDP. And this is actually really helpful in making sure that man-in-the-middles will not happen between browser A and B. But remember, this is only one part. You need to set up an identity provider in any WebRTC infrastructure, but you also have to make sure that no JavaScript is running on your endpoints, because untrusted JavaScript will actually ruin the whole security guarantees you get, for instance, by this technology. This is what you do when you set up your own WebRTC infrastructure. But of course, we can go one step further. What is actually the impact if you don't have WebRTC at all at your application? I think for most of the people present here, if you have running web applications, that will be in the case that you're running already your application, your clients now have WebRTC technology, and what is the impact of that on your application? And we'll mention two things. The first one is already known for quite a while. It means that if you have the ability to run JavaScript within your browser, and again, the best practice is not to have any untrusted JavaScript running in your application, it is able to do ICE-based fingerprinting. So it can actually collect all the local network addresses attached to your device. And based on that, this is the first step to actually trying to reconnaissance on the network to see what other services are running, or you're actually in a corporate network and so on. This is something that is already, for instance, implemented in the Beef exploitation framework. This is something that attackers were doing before by all kind of timing attacks, and now all of a sudden they have direct access to all the IP addresses belonging to your device. So to give you an idea, an ICE candidate could look like this, where you actually clearly see it's a UDP with a certain IP address and a certain port. It actually, there are websites being set up that actually, whenever you surf to that website, are using already the WebRTC technology in your browser and say these are the different IP addresses. This is a slightly modified screenshot of my own PC at work. You see a public IP address I have for my computer. You see the VPN address, and you also see my IPv6 address. So all that information is readily available to a JavaScript call directly within the browser. It will not notify me in any way. Every attacker can already do that the moment they are running JavaScript in the browser. You could say, well, it's not so big of a problem because you already know at least one of the IP addresses when you're communicating to that party. That's true, but often this is the first step to attack a local network. To attack a corporate network, you're already seeing that I'm behind a VPN, you have the local IP addresses, you can do the next step in attacking the network. Maybe a little bit more important is to mention that there are other weaknesses within WebRTC that can also have a big influence on your existing web applications and your existing user base. And I didn't find a very good title for the last attack I want to present in my presentation, but for now let's call it the holy grail of giving up all online privacy. And this is also one of the first times that we are mentioning this kind of attack to a broader audience. This is something that we recently found in one of our research experiments. It is all to do with how you're actually using the identity provider. I already showed you the image while you are interacting with the identity provider. You're running some JavaScript code of your identity provider within the context of your browser, and that code is actually generating assertions and verifying assertions. What does the specification actually say about the identity provider? The first thing is, the identity provider in no way is allowed to have user interaction. So the identity provider should not harm the way you're interacting with your user. It might not have any dialogue, any iframe, or any pop-up. They should not be interacting the identity provider with your end user. So the direct consequence of that is, if you want to use an identity provider within WebRTC, either your user is already logged in, and you could already use existing state, such as cookies, or local storage, or anything else, to authenticate the user and to generate the identity assertion. In case that the user is not logged in yet on your service, you have to fail your authentication, and you can provide a URL to the application code to say, if you want to re-authenticate with this identity provider, you might use this URL in an iframe, but you're not obliged to. It's really up to the signaling code, to the code of your WebRTC application, whether or not to load the authentication URL. This is the way you have to interact with IDP. What does this mean in practice? If you are not logged in your application, the application will know a URL where it actually can ask you to authenticate, for instance, to Google or to Facebook. But if you're already logged in into, for instance, Google, it will generate you an identity assertion automatically, and it will also include in the identity assertion explicitly the string username at the domain of the identity provider. So you will know that, for instance, Lieven Desmet at gmail.com is being authenticated by Google. This could be used, of course, by an attacker, because now all of a sudden we are able to see which is the user actually surfing to our website. So if you want to say goodbye to online privacy, think about some malicious JavaScript code being out in the wild that creates automatic identities assertions. So any browser that has already the IDP implemented in the browser could trigger automatic identity assertions. What an attacker then has to do is to be extracting your online identity from the identity assertion. So it actually asks you to authenticate to Google. You get the string in the identity assertion saying username at domain, and you can already link that information to your user. This is actually gold for a lot of companies within the internet. Think about all the advertisers that we have nowadays in our browsers. I think a lot of you might be using AdBlock or anything else, but think about the profile that they are trying to set up about the end users. They're knowing your behavior, what type of sites you're visiting, what kind of profile your user is. Now all of a sudden, an attacker with this kind of attack can link that profile to an email address or to an identity with an online provider. So even if you're using multiple devices, all those different profiles can be linked together to the same user. And actually, it's a little bit worse than that as well. Think about the malicious code that knows a set of very popular identity providers. So I would say we start with Google and Facebook, but we can list up to 100 identity providers. What we do is we actually iterate over each of them, and we look in what of the identity providers the user already was logged in before in your browser, and we typically have our browsers open for a very, very long time. And every identity assertion I get, I can link it to a previous identity assertion. And everything can run without anything triggering in the browser, without any notification to the end user, without any dialogue. And now all of a sudden, the profile of our surfing behavior we want to protect as good as possible and make it as private as possible can now be linked to exact identities of multiple online providers. And I hope that this is also the reason why we can wait for the further implementation of the identity providers, and we are currently interacting with the specification writers to make sure that this cannot happen as well. Because this is really a crucial part. If this really ships within the browsers, if we really have identity providers being present already answering those assertions, this will be really killing the whole private browsing behavior we have currently in the web. And with that, I think we can go to the wrap-up. So I have some take-home messages based on the presentation. I know I presented quite some content within this presentation, so I hope you have some time to digest what WebRTC is all about, what are the security consequences. But I think one of the take-home messages I want to say is, the first one is, it's one of the first technologies really changing the pattern we have within web applications. The client-server paradigm is broken. We now all of a sudden have a peer-to-peer fashion, and we have to take that increased attack surface into account when assessing our web applications. Also, if you see exfiltration of web applications, currently we have all kinds of tools that do exfiltration on the server side to see that no data is being leaked. Now, all of a sudden, all that data can be shipped to another browser in an encrypted peer-to-peer fashion. So all our exploitation tools might have to adapt to the new context that web browsers interact in a peer-to-peer fashion. Secondly, we saw that the web permission model is very, very liberal. So all of a sudden, your browser has become a peer-to-peer tool without needing any of your consent. Only if you're using the camera or microphone, you need consent. And for all the rest, you have a peer-to-peer tool you could use for a lot of different technologies. On the one hand, very good because it could be disruptive. On the other side, you suddenly have to think about your browser as being something very open, even behind your firewall, even behind your NAT. Third, when you're setting up WebRTC, take into account that having the encrypted link between the two browsers, the peer-to-peer link, will not authenticate by default your endpoints. You really need to set up an identity provider, and we're currently waiting until the technology arrives in the browsers. But when it arrives, and when that bug I mentioned in the last part is fixed, you really have to make sure that you're using an identity provider in your application. Other take-home message. What we saw within this presentation is something that we see quite often. When you have JavaScript running in your application, if that JavaScript cannot be trusted, it can do all funky stuff within your application. Here we saw that it could eavesdrop on media streams. it could network and identity information, but more largely, it actually can do, on behalf of the user, all kinds of functionality, even within your own application. So I think it's very good, a good best practice to limit the trust in third-party JavaScript running in your origin, in your domain, and you use all the possible best practices to protect against cross-site scripting. Quite often, cross-site scripting is said like, well, you have an alert box in your application. What can be the impact of that? Well, for instance, the exfiltration that we saw on network information on your identity, or all consequences of a possible cross-site scripting attack on your web application. But maybe the most important take-home message of today is not that we have to be very down about the whole WebRTC technology. We really have to be enthusiastic. We need to embrace a very interesting new browser capability. If I was talking about file sharing, if I was talking about very out-of-the-box conferencing possibilities within the web browser, these are really, really new browser capabilities, and we should really embrace them and be disruptive in this way. And with that, I can actually link you to a few resources talking about the assessment we did on security. So this is a public report we have on the web security and privacy assessment of WebRTC. And we also have a magazine on the new challenges for WebRTC. Both were done in the context of European project STREWS. And if you want to go a little bit broader, you also have the Clientside Web Security Handbook, which spells out what are the things to think about in setting up your web applications in a secure way. So it gets a very broad overview. What are the different characteristics you need to take into account? What are the best practices to apply in your application? And I will put the slides online so that you can find the links for further reading. And with this, I'm actually open to any question, and I hope I can answer those as well. Thank you. So, any question? Go ahead.
I have a question about WebSockets.
Yeah.
I heard you have some material on that as well from your previous colleague.
Yeah. So indeed, Philip, so the question was, do we have also material on WebSockets? Yes, indeed, we had earlier assessment, among others, WebSockets and all the HTML5 technology. Also, that's a report that you can easily fetch from INISA, but I will give you a pointer after the presentation. Any other questions? Please.
You mentioning take the identity provider, the email address, the identity. Is that exclusively about the WebRTC, or is it just JavaScript?
No, so the question is the way you actually can extract the online identity provider. Is it something really only related to WebRTC, or is it more common? The way we're typically using web identity providers, or in a single sign-on fashion, an OAuth fashion, the way WebRTC is actually using the IDP proxy is new. So this is really a new way of interacting with identity providers. So even if the browser is not implementing it yet, at the same time, also the identity provider does not have yet the APIs present to interact and give you the proxy for the IDP. So this is something that will come up, but this is really WebRTC specific. And in this sense, I also hope that we can change the way it interacts to make sure that that information is not leaking to the general public. Any other question? So thank you for your attention, and don't forget to vote. Thank you.